In this video, we will take a look at some graph theory and Ramsey theory by proving that there exist structures in large enough systems. Here's the exact setup. There are 6 people at a party, and every pair is either friends or strangers, with no in-between. We must find 3 people who are all mutual friends, or 3 who are all mutual strangers. Draw a dot for each person and join every pair with an edge. We have 6 dots that are fully connected. In graph theory, this is called K sub 6. In general, K sub n is the complete graph on n vertices. N dots, with every pair of dots joined by an edge. We color an edge blue if the two are friends, and red if the two are strangers. For example, say A and B are friends. Then we color the edge from A to B blue. 3 people form a triangle of 3 edges. This one contains some friends and some strangers. What we're really looking for is a triangle whose 3 edges are all one color. In other words, a monochromatic triangle. If all 3 edges are blue, then those 3 people are mutual friends. Color all 3 red, and they're mutual strangers. In either case, we have a monochromatic triangle, and our goal is to prove that one always exists. Let's zoom in on one person, person A. A is connected to the other 5 people by 5 edges, and each edge is either blue or red. We have 5 edges, but only 2 colors. By the pigeonhole principle, at least 3 of them must be the same color. Without loss of generality, let's say that 3 of them are all blue. Now we only consider the blue edges from A and the triangle between those 3 people. Everything will depend on those 3 edges now. Suppose one of these 3 edges is blue. Say this one. Then together with the 2 blue edges to A, it completes a blue triangle. We have 3 mutual friends, and therefore we are done. So to avoid that, let's say that all 3 of these edges are red. But then the neighbors themselves form a red triangle, and then we would have 3 mutual strangers. Therefore, with 6 people, a monochromatic triangle is unavoidable. There is always going to be a group of either 3 people that are all friends or that are all strangers. It turns out that 6 is the smallest number for which this property holds. With only 5 people, you can avoid it. Seat 5 people in a pentagon and color the 5 outer edges, the friendships, blue. Then color the 5 diagonals red. Now check any triangle you like. It always uses both colors, some pentagon edges and some diagonals. So no 3 of the 5 are all friends, and no 3 are all strangers. We call it a Ramsey number. R of Mn is the smallest number of people such that there are always either m mutual friends or n mutual strangers. Therefore, R of 3 equals 6. The next natural question is going to be how large of a party must there be to have either 3 mutual friends or 4 mutual strangers? That number is R of 4. Let's begin here. We claim that any 10 people must always contain 3 mutual friends or 4 mutual strangers. Coloring the graph, that means there's either a blue triangle or a red K sub 4, which is a complete graph on 4 vertices. So therefore, the Ramsey number that we desire, we will soon show is at most 10. Then we will improve this and then show that we cannot improve it anymore. For a party of 10 people, we begin by modeling it as the complete graph on 10 people, and we zoom in on one of them. Say person A. A has 9 edges to everyone else, each either blue or red. Here's the key idea. If A has at most 3 blue edges and at most 5 red edges, then that's at most 8. But A has 9 edges coming out of it. So A must have at least 4 blue edges or at least 6 red edges. Consider the first case. If A has 4 blue edges, then any blue edge among them makes a blue triangle with A. And if there are no blue edges among these 4 neighbors, then those 4 are a red K sub 4. If instead A has 6 red neighbors, then among those 6, the result we just proved showed that there must be a monochromatic triangle. A blue one is a blue triangle that we were looking for. A red one, then combining that with vertex A, gives us a red K4. So in either case, 10 always works. Now try 9 people. To avoid the 2 cases from last time, the same count means that we must have that for every single vertex, they'll have 3 blue edges and 5 red edges. So then in this case, 3 plus 5 is 8, which is the full degree of every vertex. Now let's just look at the blue edges. That's a graph on 9 vertices where every vertex has degree 3. If we add up all those degrees, 9 times 3 is 27, which is an odd number. Now, the key fact. The handshaking lemma in graph theory, which states that the degrees always add up to exactly twice the number of edges, which is an even number. Why is that true? Well, every edge has 2 endpoints, so it adds 1 to 2 different degrees. That means each edge is counted twice in the sum of degrees, so the total is exactly 2 times the number of edges. However, 27 is odd, which cannot equal an even number. This is a contradiction. So, 9 people can't avoid it either, and R of 3, 4 is at most 9. Could the answer be even smaller? To rule 8 out, we only need to find one way to have 8 people with no 3 mutual friends and no 4 mutual strangers. Here's an example. Say that each person is friends with the 2 people directly next to them and the person opposite of them, which will be colored in blue. Every other pair is red, in other words, strangers. First, we check that there is no blue triangle. Pick anyone, say A. A has exactly 3 friends, their 2 neighbors, B and H, and the person opposite of them, E. But those 3 friends are mutual strangers. So A cannot sit in a blue triangle, and by symmetry, no one can. Now we check that there is no red K sub 4. A red K4 would mean that we need someone together with 3 of their strangers to also be strangers to another. In this case, for example, A strangers are C, D, F, and G. But among those 4, C and D are friends, and F and G are friends. So therefore, it's impossible to choose 3 of them that are all strangers to each other. Therefore, once again, we do not have a red case of 4, and by symmetry, nobody is in a red case of 4. So, this one seating avoids both. There's no blue triangle and no red K sub 4. 8 people can avoid the pattern, which means R of 3, 4 is more than 8. Putting it all together, we know that 8 people can avoid this, but 9 always contains 3 mutual friends or 4 mutual strangers. So, R of 3, 4 is exactly 9. And this pattern continues. Ramsey's theorem guarantees every one of these numbers exists. Name any 2 sizes you like, and a large enough party is forced to contain that many mutual friends or that many mutual strangers.